With the basics out of the way about water and its properties, we can start to talk about how it relates to chemistry. We're going to do that through some examples that relate to our everyday life, and then we're going to start talking about solutions. I do want a whole day to discuss acids and bases though, so we will have a third part to the series. First, let's talk about evaporative cooling. The idea here is simple. If you take a set of water molecules, let's say there's 4 of them, and we assign them some values to represent their kinetic energy, 1 being the lowest and 4 being the highest. Now let's give them a heat source. Let's say it's the sun. And each one is receiving the same amount of heat. Recall that these numbers will also mean that they had initial kinetic energy. Now let's say these numbers are constantly increasing because of the heat. The thermal energy from here is getting transferred in the form of heat to increase the thermal energy of all the other molecules. If there was some threshold kinetic energy value that would allow the molecules to evaporate, let's say that value is 8, then obviously the one with the highest starting number will reach 8 first and evaporate. That means that the water molecules that have the highest kinetic energy, remember that's what those numbers represent, evaporate first. As a result of this, if we now look at the average kinetic energy, with these 4 values, the average is 2.5. But when this one at the end evaporates, the new average is only 2. So the average kinetic energy has decreased. And if you'll remember from our last lesson, the average kinetic energy is nothing but the temperature of the entire body of water. You'll also see examples of this when you look at an elephant blowing water on itself, or an even more relatable example, humans sweating. The reason we sweat is that when that sweat evaporates, it helps us cool off, because the temperature of the surface is decreasing. Next, let's talk about density. Density is a measure of how much mass there is in a certain unit of volume. It's usually measured by our common unit of mass, G, by our common unit of volume, L, grams per liter, or any variation, grams per milliliter, milligrams per milliliter, etc. Remember that chemistry and biology favor the metric system. In fact, all science favors the metric system, so it's best to get used to it now. Let's take this unit of volume for substance A, and another unit of volume, which we'll say is the exact same amount, for substance B. Let's say in that unit of volume, A has 2 grams, whereas B has 4 grams. All this means is that A has 2 grams per unit of volume, we'll say milliliter, whereas B has 4 grams per the same unit. Most substances, as you might be able to imagine, are denser as solids than as liquids. If you take a look at some liquid on the ground and some molecules in there to represent the mass, it's more likely that these particles will start to condense inwards to form a solid. But not water. Of course, that's a very common phrase, but not water in these lessons. And another thing that's a trend is the reason for that. Of course, in our case, the reason is hydrogen bonding. Because the reason with these properties, as we know already, a lot of times is hydrogen bonding. Let's have a few bonds like so. All right. If you take a look at the water molecules as a whole, you'll see that in ice, they arrange themselves in a crystalline structure, with these hydrogen bonds connecting them. That's because of the way that these molecules have to be positioned to have these bonds. Water is always trying to maximize the number of hydrogen bonds in solid form, which is why it's the hardest of the forms. But the trade-off is that it's not as dense, because in trying to make this crystal structure, there are some air pockets that are left. So actually, ice, which is solid water, is less dense than water. This is a good time to mention something about writing chemical formulas. Especially in reactions, if you add parentheses at the end and use the letter S, L, G, or AQ, that's referring to the state of matter. S for solid, L for liquid, G for gas, and AQ for aqueous solution, which I'm going to talk about right now, I think. A completely homogeneous liquid is what we call a solution. Homogeneous means that if I take this liquid and I take a look inside and pick two random sections, right? Let's take this section and this section. The contents of those sections should be almost identical. That means that everything in that mixture or solution is scattered and distributed evenly throughout. There's two types, or rather two parts for a solution. There's the solute, which is going to be represented like this, and the solvent. The solute gets dissolved in the solvent. So the solute is the thing that gets dissolved, the solvent is the thing that dissolves. And once that's done, the product is a solution. The solute dissolved in the solvent. But what about water? Where does that come in? Well, water is actually considered a universal solvent because it can dissolve most ions and polar compounds, and even has effects on nonpolar compounds. The way this works is, let's take this molecule here, NaCl. This is an ionic compound, and it represents table salt, sodium chloride. The sodium ions and the chlorine ions, the chloride ions, have to separate somehow. The way it's done is that the water molecules surround them and form a kind of hydration shell, which separates the two. But again, what's the reason for this? Well, if chlorine is negatively charged as an ion, if you remember the term anion, then only the positive end of the water could form any kind of interaction with it, because opposite charges attract or interact. So the hydrogen is positioned towards it, whereas sodium has a positively charged ion, meaning we need the negative side of the water molecule to interact with it. So far, so good. These hydration shells will separate the ions from each other. The resulting solution is with water as the solvent and sodium chloride, NaCl, as the solute. So here's sodium chloride before it gets inserted. And afterwards, it'll dissociate into sodium ions and chloride ions, separated by our hydration shells. This kind of solution, where water is the solvent, is what we call an aqueous solution. It's represented by AQ, and if you want to know how to spell it, it's aqueous solution. Like that. Depending on whether or not a substance interacts with water like this, we can call it either hydrophilic, which means loving water, or hydrophobic, which means hating water. These are derived from Greek terms. Hydrophilic meaning that it will interact strongly with water, whereas hydrophobic means it will not interact at all with water. The last concept I want to talk about here is like dissolves like before we move on. Like dissolves like is this idea that polar molecules are going to be better at dissolving other polar molecules, and nonpolar molecules will have the same thing with nonpolar molecules. While this doesn't always hold, and it's not a valid assumption to use when dealing with actual chemistry, for the purposes of biology, this is more than sufficient. So we'll use this theory in most of our problem solving from here on out. That means that hydrophilic substances are usually polar, and hydrophobic substances are usually nonpolar. And vice versa. Nonpolar substances are usually hydrophobic, polar substances are usually hydrophilic. The last thing to talk about is the difference between solubility and concentration. Solubility and concentration get interchanged so often, but they're actually really different things. They're almost both like measurements of density for a solution, which doesn't make a lot of sense right now, but it is the same concept of mass over volume. In this case, though, it's mass of solute over volume of solvent. So, concentration is a measure of how much solute in a solution. Let's call this solution A. It's how much solute in how much solvent. For example, if we take sodium chloride again, we can say the concentration in a random solution is 3 grams per milliliter. Next, let's look at solubility. Solubility is not based on a specific solution, rather, it's based on a specific solute and solvent pair. And you might be wondering, hey, doesn't that mean the exact same thing? Not entirely. If I said the solubility of NaCl in water was something, let's say 20 grams per milliliter, that would mean that in 1 milliliter of water, you can, here's our keyword, can dissolve up to 20 grams of sodium chloride. After that, it won't dissolve anymore. If I add another gram, it won't dissolve in that water. However, concentration of sodium chloride in water being 3 grams per milliliter, that basically suggests the existence of a solution that has this amount of sodium chloride per this amount of water. So, while concentration refers to a present state, solubility is more of a hypothetical state. It's basically the maximum concentration. And last bit of information here, putting something in these square brackets means the concentration of that thing. So this means concentration of sodium chloride. So the maximum concentration is solubility, whereas the existing amount of solute per solvent is concentration.